alhamdulillah hamaरे डॉक्टर ने साथ में
Today we will be studying eigenvalues and eigenvectors of a matrix. We begin with the definition and then we take a look at the method of finding the eigenvalues and eigenvectors of a matrix. So let's start with the definition. Let A be a square matrix of order n. Eigenvalues and eigenvectors will always be defined in the context of a square matrix. So we begin with the square matrix of order n. A scalar lambda is called an eigenvalue of A if there exists a non-zero column vector x such that A into x is equal to lambda times x. For us, a scalar, as I mentioned earlier, for us a scalar will be a real number. But in this particular case, when I say lambda is a scalar, lambda could either be a real number or in some cases it could even turn out to be a complex number. So here by a scalar we mean either a real number or a complex number. A little later I will tell you why lambda could also be a complex number. So any such number lambda will be called an eigenvalue of A if there exists a non-zero column vector, that means a non-zero column matrix X for which this equation is satisfied, and X is called an eigenvector of A. Corresponding to an eigenvalue lambda. Corresponding to the eigenvalue lambda. Now here is something very important that one has to know, and that is this vector x is never allowed to be the zero vector. Now the reason why we are looking for a non-zero column matrix which will satisfy this equation is the following. If at all I allow x to be the zero matrix, see what would happen. If I allow x to be the zero matrix, then no matter what matrix A I take, A into x will be A into the zero matrix, and any matrix multiplied by the zero matrix is the zero matrix. Also, any scalar lambda into the zero matrix will be the zero matrix. That means if I allow x to be 0, then for any square matrix A into x will be the 0 matrix, and for any lambda into x will be the 0 matrix. That means this equation will be satisfied for any lambda, and therefore every scalar will be an eigenvalue of A. So there is nothing dependent on this matrix. For any matrix, any scalar will become an eigenvalue, and we surely don't want that to happen. We want the eigenvalue to have something to do with that matrix. So depending on what that matrix is, accordingly we must get a value of lambda, and that's why we don't allow x to be the zero matrix. It's simply to avoid every scalar from becoming an eigenvalue of every matrix. So the definition is a scalar lambda will be called satisfy this equation, and such an x is called an eigenvector of A. Other names for eigenvalues are proper values, or we can call it a latent root, or even a characteristic root. So these are certain other names given to an eigenvalue of a matrix. So let's look at an example before I tell you how exactly to find an eigenvalue of a matrix. Suppose I take A to be the matrix 3, 0, 8, -1, and X to be the column matrix 1, 2. Then A into X will be 3, 0, 8, -1 into 1, 2. If I multiply these two matrices, I get 3 into 1 plus 0 into 2, 8 into 1, -2, that is 6, which will work out to be 3 times 1, 2, which is 3 times x. So A into x is 3 times x. Therefore, lambda equal to 3 becomes an eigenvalue of it. Because there is a non-zero vector x for which the equation Ax equal to 3 times x is satisfied. So this scalar 3 is an eigenvalue of this matrix, and x equal to 1, 2, the vector x is an eigenvector of A, corresponding to the eigenvalue lambda equal to 3. So this example should convince you that one can, or at least it explains the concept of eigenvalue and eigenvector further. Let me remind you that the eigenvector is never allowed to be equal to 0. However, the eigenvalue could be 0, but the eigenvector by definition is never allowed to be equal to 0. Now, in this example, notice that I gave you a vector and we only made sure that it becomes an eigenvector of it. However, given a matrix A, our problem should be how do we go about finding eigenvalues and eigenvectors. Surely this is not the correct approach where we try out all possible vectors, see for which vector this kind of an equation is satisfied, because there will be infinitely many such vectors. So we need a proper method to find the eigenvalues and the eigenvectors of a matrix. Let us first see how to go about finding all possible eigenvalues of a matrix. Come to the system of linear equations. There was a particular result that I had mentioned. I will recall that over here before I go to the next result. Suppose I take A to be a square matrix of order n. Then we know that the homogeneous system, then in fact we have done this in lecture number 4. Then the homogeneous system Ax equal to capital O has a non-trivial solution if and only if determinant of the coefficient matrix is equal to 0. For a homogeneous system, if you remember, I had mentioned that there are only two possibilities. Either you can have one solution, in which case it is the trivial solution, or you can have infinitely many solutions. A homogeneous system is never inconsistent. So when we result. This says, let A be a square matrix of order n. A scalar lambda is an eigenvalue of A. If and only if determinant of A minus lambda times I is equal to 0. So let us first just concentrate on proving this result. So we have a square matrix. A scalar lambda is an eigenvalue of A. Recall the definition. A scalar lambda will be called an eigenvalue of A if and only if there exists a non-zero vector x which will satisfy the equation Ax equal to lambda x. Remember, we have to find a non-zero solution to this equation. So let me simplify this further. If and only if there will exist a non-zero vector x such that Ax minus lambda times. Now in place of this x, I can write identity times x, because identity matrix into any matrix is the same matrix, and therefore in place of x I can write identity times x. Let me simplify this further. So this will happen if and only if there exists a non-zero vector x such that A minus lambda I times x is equal to capital O. If temporarily I call this as capital P, this looks like Px equal to capital O, which means this is a homogeneous system, and what I am looking for is a non-zero, a non-trivial solution to this homogeneous system. Now make use of the previous note. The previous note says that such a homogeneous system will have a non-trivial solution if and only if determinant of the coefficient matrix is 0. So in this case, this will happen if and only if determinant of the coefficient matrix, which is A minus lambda I, this should be equal to 0. And there we are. That gives us a method to find the eigenvalues of a matrix. If we expand from the examples it will be clear that if we expand this expression determinant A minus lambda I, this works out to be a polynomial in lambda. This will be a polynomial in lambda of degree n. So if A is a square matrix of order n, determinant of A minus lambda I is going to be a polynomial in lambda of degree n, and this will be called the characteristic polynomial of A. So if I look at determinant of A minus lambda I equal to 0, this being an equation, this is called the characteristic equation of A. And the previous result tells us that a scalar lambda is an eigenvalue of A if and only if this equation is satisfied. So if I am interested in finding the eigenvalues of any matrix, what I need to do is to first get the characteristic equation of A. It's going to be a polynomial equation in lambda of degree n, and we know that a polynomial equation of degree n has exactly n roots. So this is going to be a polynomial equation in lambda of degree n. It has exactly n roots. These will be called the characteristic roots, or these are the eigenvalues of A. So notice that if it is a square matrix of order n, we will get exactly n eigenvalues. Of course, some of them could be repeated. Also, roots of a polynomial equation can be real numbers or complex numbers. That's why right in the beginning in the definition I mentioned that when I say a scalar lambda is an eigenvalue, because it's going to be a root of this polynomial equation, it could be either a real number or it could be a complex number. So in order to find the eigenvalues of a matrix, get the characteristic equation, solve that, the roots of this characteristic equation will give us the eigenvalues of it. Let us first just concentrate on finding the eigenvalues. Once we are thorough with this, then we will look at the eigenvectors of it. So let's work out the problem on finding the eigenvalues of a matrix. Let's start with a simple case. We'll take a 2 by 2 matrix to begin with. So here's the problem. Find the eigenvalues of A equal to 1, 4, 3. To find the eigenvalues, we need the characteristic equation. So let's begin with the characteristic equation. The characteristic equation of A is determinant of A minus lambda I equal to 0. That means it will be determinant of A is 1, 4, 3, 2 minus lambda times the identity matrix. Determinant of all is equal to 0. That means we have determinant of 1, 4, 3, 2. And that means we get determinant of 1 minus lambda, 4 minus 0, 3 minus 0, 2 minus lambda. In fact, it's not really worthwhile doing these steps. If you can check what is the relationship between this matrix and this matrix. Notice that because it is lambda times the identity matrix, when I do the scalar multiplication, I get a diagonal matrix in which I have lambda along the diagonal. It's a diagonal matrix, so all other entries are zeros. So when I do this matrix minus this, from the original matrix, all I need to do is subtract lambda from each diagonal element. So henceforth, when I write the characteristic equation, I'll skip these two steps. All I need to do is take the determinant of the matrix which is obtained from A by subtracting lambda from the diagonal elements. So let us evaluate this. So the characteristic equation of this matrix is going to be determinant of 1 minus lambda, 4, 3, 2 minus lambda equal to 0. If we expand this, we get product of the diagonal elements minus product of the non-diagonal elements. Let's open out the brackets. 2 minus lambda minus 2 lambda plus lambda square minus 12 equal to 0. So we get lambda square minus 3 lambda minus 10 equal to 0. And the factors of minus 10, we get minus 5 and plus 2. So that we have lambda into lambda minus 5 plus 2 times lambda minus 5 equal to 0. That means lambda minus 5 common into lambda plus 2 equal to 0. So lambda is equal to 5 or lambda is equal to minus 2. See, as I mentioned earlier, if we start with the square matrix of order 2, have to first form the characteristic equation, and the characteristic equation of a matrix is determinant of A minus lambda I equal to 0. As I mentioned earlier, we can save some time over here. All you need to do is to take determinant of, keep this whole thing as it is. Just subtract lambda from each diagonal element. So it will be determinant of minus 2 minus lambda. These two entries will remain the same. Again from the diagonal elements subtract lambda. Minus 6. Then we have minus 1, minus 2. 0 minus lambda will give us minus lambda equal to 0. So all you need to do is to subtract lambda from every element along the diagonal of A and take determinant of that matrix. Now if I expand this, I'll get minus 2 minus lambda into this 1 minus lambda into minus lambda minus this into this minus 2. You could write up on your own this into this minus 2 lambda minus 6 minus 3 into this into this minus this into this equal to 0. I have already carried out the expansion. I will give you the polynomial. This time remember is the matrix of order 3. So the characteristic equation has to be a polynomial equation in lambda of degree 3. And this is the equation that I get after simplification. In fact, I can take a minus sign to the other side so that it is lambda cube plus lambda square minus 21 lambda minus 45. Of course, minus 0 is the same as 0. For quadratic equation, there are direct methods of solving. You can either factorize directly or worst case situation. You can always use the formula minus b plus or minus under root b square minus 4ac upon 2a. So for a quadratic equation, finding the roots is never a problem. For a quadratic equation, if you cannot factorize directly, you can always use this formula. With the plus sign, you will get one root. With the minus sign, you will get the other root. The problem is what does one do when one has a cubic equation? For a cubic equation, hopefully the problems that will be given to you will be such that it will be easy to find at least one of the roots by trial and error. What you need to do is try out lambda equal to 1, see if the equation is satisfied. If not, try lambda equal to minus 1. If not, then try lambda equal to plus 2, try lambda equal to minus 2, and so on till you hit upon the root. Now here, if I put lambda equal to 5, if I put lambda equal to 5 in this, I'll get 5 cube plus 5 square minus 21 into 5 minus 45, which will work out to be 125 plus 25 minus 105 minus 45, that is 150 minus 150 equal to 0. So if I put lambda equal to 5, the equation is definitely satisfied, which means lambda equal to 5 is one root of this equation. Now by the method of synthetic division, we will first find the associated quadratic equation and then solve it. All one has to do is to write the coefficients in that order without missing any of them. So 1, 1, minus 21, minus 45. We already know that 5 is a root. Always start with the 0. 1 plus 0, 1. 1 into 5, 1 into 5 is 5. 1 plus 5 is 6. Then 6 into 5. 6 into 5 is 30. Minus 21 plus 30 is 9. And 9 5s is 45. At the end, if all your calculations are correct so far, this last term has to be 0. That means your calculations are correct. And this will tell you what is the associated quadratic. So this will be be 1 into lambda square plus 6 lambda plus 9 equal to 0. And this in fact is a perfect square. This is lambda plus 3 the whole square equal to 0. The two roots of this equation are lambda equal to minus. Two of the roots are identical. As I mentioned earlier, this is a cubic equation. Totally there will be three roots, some of which can be identical. So in this case, we have got lambda equal to 5, minus 3 minus 3. These are the eigenvalues of it. So given for the 3 by 3 matrix, it's not going to be too difficult to find the eigenvalues. Obtain the characteristic equation first. If it's a 3 by 3 matrix, you get a cubic equation. Find one root by trial and error. Then you can use syntactic division to get the associated quadratic, and then get the other two roots. So in all, for a square matrix of order 3, at the end, you must get 3 eigenvalues. Probably some of them, as you can see in this case, may be repeated. There are also cases where you may end up with complex roots, but in your syllabus I don't think there are such problems. But not to worry, because these are just roots of a polynomial equation. They can be real numbers, they could also be complex numbers. Before we go on to find eigenvectors of a matrix, there are certain interesting problems, rather interesting properties of eigenvalues. Let's take a look at some of them over here. The first property is any square matrix A and its transpose, any square matrix A and its transpose A raised to T have the same eigenvalues. Remember, transpose of a matrix is obtained by interchanging the rows and columns of A. So this result tells us that for any square matrix, the eigenvalues of A and its transpose will always be the same. Well, it's not really difficult to prove. All you have to do is use properties of the transpose. Let's first try and find the eigenvalues of A transpose. Just recall the problems, exactly what method we employed over there. We have to obtain the characteristic equation first and then get its roots. So let me first check out what is the characteristic polynomial of A transpose. The characteristic polynomial of A transpose by definition is determinant of A transpose minus lambda times I. Notice that transpose of the identity matrix is the same as the identity matrix, because in an identity matrix is a symmetric matrix. So even if I interchange the rows and the columns, I'll get back the same matrix. That's why in place of I can write I transpose. And now I'm going to use some of the properties of the transpose. One of the properties was you can first take the transpose and then multiply by the scalar, or you could first multiply by the scalar and then take the transpose. And we also know that difference of the transposes is transpose of the difference. So this will be determinant of transpose of A minus lambda I. And determinant of the transpose of a matrix is the same as the determinant of that matrix. So this will be the same as determinant of A minus lambda I. And that is nothing but the characteristic polynomial of A. So notice that the characteristic polynomial of A transpose and characteristic polynomial of A are the same. And the characteristic polynomials of the the same. So that is one of the interesting properties. Let's take a look at some more properties. The next one especially is going to make our life a lot easier for at least some of the matrices. The result says, if A is a triangular matrix, if A is a triangular matrix, then the eigenvalues of A are precisely the elements on the principal diagonal of A. So if I take a triangular matrix and at a glance one can make out whether it's a triangular matrix or no. So if I have a triangular matrix, then this is a very handy result to use. This says if you need the eigenvalues of such a matrix, all you have to do is read the elements along the main diagonal of A, and they will be precisely the eigenvalues of A. Now when I say a triangular matrix, remember it could either be an upper triangular matrix or it could be a lower triangular matrix. It doesn't really matter which way I start with it. I could do the result for an upper triangular matrix, and similarly you could work it out for a lower triangular matrix. So let me just take A to be an upper triangular matrix. So let me take a general upper triangular matrix of order n. Such a matrix will look like A11, A12, A13, A1n. Then we have 0, A22, A23, A2n, 0, 0. This should be ANN. Remember, in an upper triangular matrix, all elements below the main diagonal have to be zeros. So suppose A is an upper triangular matrix, it will look somewhat like this. The characteristic equation of A will be determinant of A minus lambda I equal to 0. And I told you a very easy method of going to this equation directly. All you have to do is subtract lambda from every element along the diagonal and then take the determinant. So what we get is A11 minus lambda, A12, A13, A1n, 0, A22 minus lambda, A23, A2n, 0, 0. This will be ANN minus lambda. And for a triangular matrix, we know how to get the determinant. The determinant is nothing but the product of the diagonal elements. So for this matrix, the determinant is going to be A11 minus lambda. Just multiply the entries along the diagonal. ANN minus lambda equal to 0. And don't bother to open this out, it's already factorized. If you open it out, you will have to once again factorize it and get the roots. So don't do that, it's already factorized. Equate each factor to 0. We get lambda equal to A11 or lambda equal to A22 or lambda equal to ANN. So these are the eigenvalues of A. And notice that these are nothing but the elements along the main diagonal of A. So for a triangular matrix, here I put the result for an upper triangular matrix, but you can see that if it's a lower triangular matrix, this property of the determinant of a triangular matrix is product of the diagonal elements lambda raised to n is an eigenvalue of a raised to n for all natural numbers n. This stands for the set of all natural numbers. So it will be lambda square is an eigenvalue of a square, lambda cube is an eigenvalue of a cube, and so on. So what you need to do is, suppose lambda is an eigenvalue of a, there will be some non-zero vector x which will satisfy this equation. Surprisingly, the same eigenvector is going to work for this case also. So what we have to do is to prove that a raised to n times x is equal to lambda raised to n times x for all natural numbers. And whenever you wish to prove a property regarding all natural numbers, a simple way out is to make use of mathematical induction. So you will make use of induction and prove this result. Let's look at an application of this. Find the eigenvalues of a raised to 5. If a is equal to 1, 3, 0, minus 3, 4, 0, 0, minus 1. Find the eigenvalues of a raised to 5 if a is this matrix. Now the first thing I should do is to find the eigenvalues of a. See if you can do that. For finding the eigenvalues, one must, under usual circumstances, take a look at the characteristic equation and solve it. But you don't really have to do it by that method over here. See, this is a triangular matrix. All elements below the diagonal are zeros. And remember the result that we proved just now. For a triangular matrix, you can orally tell me what are the eigenvalues. The elements on the main diagonal are precisely the eigenvalues of A. So the three eigenvalues of A, if I call them as lambda 1, lambda 2, lambda 3, the eigenvalues of A are lambda 1 equal to 2, lambda 2 equal to minus 3, lambda 3 equal to minus 1. So eigenvalues of A are 2, minus 3, minus 1. And now make use of the note, the result which I did not prove, I only mentioned. And that is, if lambda is an eigenvalue of A, then lambda raised to n is an eigenvalue of A raised to n. So if I want eigenvalues of A raised to 5, there will be lambda 1 raised to 5, that is 2 raised to 5, 32, minus 3 raised to 5, minus 3 raised to 5 is going to be, whatever that works out to be. You can do the calculations later. And I think it's 243, minus 243. And lambda 3 will be minus 1 raised to 5. That will be minus 1. So eigenvalues of A raised to 5 are 32, minus 243 and minus 1. Also the next property, I think I'll just mention over here. It's not going to be difficult to prove it. If lambda not equal to 0 is an eigenvalue of an invertible matrix A, is an eigenvalue of an invertible matrix A, then 1 upon lambda is an eigenvalue of A. Not very difficult to prove. You just have to use the definition of inverse of a matrix and of course the definition of eigenvalues and eigenvectors. Now here once again I will remind you that the definition of eigenvalue says that there should be a non-zero vector x which will satisfy this equation. Now for reasons that I mentioned earlier, x is never allowed to be equal to 0. So by definition, an eigenvector is always non-zero. However, the eigenvalue may be 0 if also called the trace of the matrix. And product of the eigenvalues is nothing but the determinant of the matrix. So that should, by the way, tell you why an invertible matrix can never have 0 as an eigenvalue. Because if A is invertible, the determinant cannot be equal to 0. And if you want this product to be non-zero, each and every term in this product has to be non-zero. So an invertible matrix can never have 0 as an eigenvalue. Let's try and put all these results together and see how this would be used in a problem. So let's try out this. Two eigenvalues of A equal to 2, 2, 1, 1, 3, 1, 1, 2, 2 are equal to 1 each. Find the eigenvalues of A inverse. Now this being a 3 by 3 matrix, notice that it will have 3 eigenvalues. Let me take the 3 eigenvalues of this matrix to be lambda 1, lambda 2 and lambda 3. See what else is given. It's given that 2 of them are equal to 1. Let me take lambda 1 equal to 1, lambda 2 equal to 1, and at the moment I don't know the value of lambda 3. Now let me make use of the earlier note. The earlier note says that the sum of the eigenvalues is equal to the trace of the matrix. Trace of the matrix is the sum of the diagonal elements. So if I make use of that note, then lambda 1 plus lambda 2 plus lambda 3 will be 2 plus 3 plus 2. We know the value of lambda 1. We know the value of lambda 2. This will be 7. So lambda 3 will be equal to 5. And once you know the eigenvalues of A, just take their reciprocals, you get the eigenvalues of A inverse. So eigenvalues of A inverse will be, eigenvalues of A inverse are 1, 1 and 1 by 5. And before we wind up this session, as I had promised, we'll see a method for finding the eigenvectors of a matrix, and we'll work out at least one problem in class. For lambda to be an eigenvalue of A, I must get a non-zero vector x for which Ax will be equal to lambda x. In fact, I have done the simplification before. For x, I can always write identity times x, because identity into any matrix is the same matrix, and that means A minus lambda I times x is equal to 0. So what I am doing is to look for a solution of this homogeneous system. So in order to find eigenvectors of a matrix, once you have identified the eigenvalues for each eigenvalue, for each value of lambda that you put over here, you get one homogeneous system. Solve that homogeneous system. In fact, it will have infinitely many solutions. Any one of those infinitely many solutions, any one of those non-zero infinitely many solutions will give us eigenvectors of A corresponding to that particular eigenvalue. So let's actually work out the problem. To save time, I am going to make use of the same matrix whose eigenvalue find the eigenvalues and the eigenvectors of the matrix A equal to -2, 2 minus 3, 2, 1, minus 6, minus 1, minus 2, 0. Remember what one has to do? Look at first find the eigenvalues. So look at the characteristic equation. Characteristic equation of A is determinant of A minus lambda I times x equal to 0. Determinant of A minus lambda I equal to 0. That means it will be determinant of -2 minus lambda, 2 minus 3, 2, 1 minus lambda, -6, -1, -2, 0 minus lambda. So this is the characteristic equation. Then we solve this characteristic equation and we got the three eigenvalues. Lambda equal to 5, -3, -3. Now for each of these eigenvalues, I am going to find the corresponding eigenvector. So let us start with lambda equal to 5. As I mentioned in the note, for each eigenvalue, you have to look at the system A minus lambda I times x equal to capital O. This is determinant of A minus lambda I. So A minus lambda I is the matrix -2 minus lambda, 2 minus 3, 2, 1 minus lambda, -6, -1, -2, minus lambda. And let me take x to be x, y, z equal to the 0 matrix. Now, I need to do this specifically for lambda equal to 5. So, when I put lambda equal to 5 in this, my homogeneous system is going to look like -2 minus 5, -7, 2, -3, 2, -4, -6, -1, -2, -5. X, Y, Z. In the earlier sessions, we have spent enough time on reducing the matrix to the echelon form. So I am not going to waste any more time over here. The idea is to tell you how to find the eigenvector. So I'll give you the echelon form for this. If we reduce this matrix, we get 1, -14, -27, 0, 1, 2, 0, 0, 0. This of course remains as it is for a homogeneous system. So if I rewrite the system of equations, I'll get x minus 14, y minus 27, z equal to 0 and y plus 2z equal to 0. There are two equations and three unknowns. Since there are two equations and three unknowns, one of them will be a free variable. Let us put z as the free variable. So in that case, y will be equal to -2x, and from the first equation we get x equal to 14y plus 27z. So x will be -28 plus 27. X will be -s. So if we look at the vector x, it will be -x, -2x and s. So that is s times -1, -2, 1. So you will notice that because of this free variable, there are infinitely many eigenvectors corresponding to the eigenvalue lambda equal to 5. If you are just interested in one eigenvector, you can accordingly put a value for s. Now, when you are checking your answers for eigenvectors from the textbook, you could differ in this multiple. So long as by taking over here. So accordingly the answer in the book could be different. It's not wrong. You just have to take whatever multiple you want because there are infinitely many solutions. Pick any one of them. Each one of them is an eigenvector corresponding to that particular eigenvalue. In this case, corresponding to lambda equal to 5. Now one has to repeat the whole story for the eigenvalue lambda equal to -3. So let us now find an eigenvector corresponding to lambda equal to -3. We go back to this equation and this time, remember we are trying to find the eigenvector corresponding to lambda equal to -3. So let me put lambda equal to -3 in this. I'll get -2 plus 3, 1, 2, -3, then 2, 4, -6, -1, -2, 3. And after I reduce this to the echelon form, I think I'm going to get this. Let me confirm. Yes. So after reducing this to the echelon form, this time we are left with only one equation. Now, when you have a repeated root, one of the two possibilities will occur. I'll talk about that at the end. See, there is only one equation and two unknowns. So, two of them are going to be free variables. Let me put y as s and z as t. Then x will be -2y plus 3. So, our solution vector x is going to be x, y and z. Let me separate the constants s and t. So -2s, s 0 plus 3t, 0 t. And if I get s from the first matrix, it will be -2, 1, 0. And t common from the second matrix, that will give me 3, 0, 1. Now, for different combinations of s and t, I'll get different eigenvectors, and the two eigenvectors that I'll get, one combination is put s equal to 1, t equal to 0. So I'll get -2, 1, 0, and put s equal to 0, t equal to 1. I'll get 3, 0, 1. Now I don't want to go into the pure mathematics of this, but keep in mind that if you have two free variables, you will get two linearly independent eigenvectors. These are what are called as linearly independent eigenvectors. This is not a multiple of this, nor is this a multiple of this. Whereas in the earlier case for lambda equal to 5, if I take any other eigenvector, it's going to be a multiple of the vector that I had written. However, that's not the case over here. So if there are two free variables, you will get two linearly independent eigenvectors. So for the matrix A, I got three different eigenvectors in all. For lambda equal to -3, this was a repeated eigenvalue. For a repeated eigenvalue, if this is repeated twice, depending on the situation, you may either get only one linearly independent eigenvector corresponding to this, or you may get two independent eigenvectors as we have got in this case. So it all depends on how many free variables are left at the end. With that, we have finished the article on linear algebra. So unit 3 is done. That's all for today. It was exactly 1 hour.
3 seconds. 3 seconds.